Hi, hello guys. This is the continuation of the previous problem, but on another problem. And on the previous problem, we made a mistake. Instead of getting an answer of 0,0375, we got 0,075. It is because of I made a mistake of dividing by 100 from the onset. I'm supposed to multiply first by VB squared, cross multiply, and then I'm left with this, and then I divide by 100. So please just correct it there for me. Just correct it there for me. Hey, we work night shift. Sometimes we are tired, and we really apologize. And this is the longest problem of all, and I hope I won't make such a mistake. It says what? And then please write it down as well. Please sometimes pause the video, write everything down, and then because there are something that I've got no choice on this one. Really, I have to delete right away. It's a very long problem, but I'm gonna use this space first for calculations. Hey guys, please subscribe there for me, share the video, like, distribute it. I will really be appreciative of that fact. A three-phase transmission line operating at 10 kilovolts and having a resistance of 1 ohm and reactance of 4 ohm is connected to the generating station through a 5 megavolt amps step-up transformer. Very important. Remember, when you start this kind of problems, always when you start them, always you have to draw the line diagram. Where do you get the line diagram? You derive a line diagram from the information given. From the information given. A step-up transformer having a reactance of 5%. These bus bars are supplied by a 10 megavolt amps alternator. This is the situation, guys. This is an alternator. We are told that it is 10 MVA, having 10% reactance. 10% reactance. Let me just write 10% reactance. This alternator, always an alternator supplies bus bars before the voltage or before the power is transferred to the line. Always it must supply the bus bars. This is a bus bar. This one, it is a bus bar. This bus bar, according to this information, it is connected to the transmission line through what? A step-up transformer. This is a step-up transformer. Okay, and it is equal to what? It is 5 MVA with a percentage reactance of how much? Percentage reactance of 5%. And then this transformer supplied what? A line having what? This line is rated at 10 kilovolts. That is the maximum voltage that can be carried by that line. Anything above that, we don't know what will happen. But it is rated at 10k according to that statement. And then this line it has what? It has a resistance of 1 ohm and a reactance of 4 ohm. This is the situation. This is the situation. And then this is called a line diagram. You derived it from the information. Very important. Otherwise, you're not gonna see what's going on there. Right. Now, calculate what? Calculate SC, the short circuit KVA. Okay, one other thing. We all know that, man, at the point of fault, the voltage is 0. But for the purpose of making sure we work with the same unit, it is in practice, it is usual practice to convert the fault or the short circuit fault to a short circuit KVA. to a short circuit kVA. It is the system voltage multiplied by the load current. But remember now, in this case, that load, that current, it is actually now a fault. It is actually a fault. So what is a short circuit kVA? Those who knows better than me and you, they call it the fault level. It is the power that flows into the fault. It's a discussion for I think Mr. Wakisan and tomorrow's problem. That problem is gonna pop up. Right. Now. Look, very, very important. Now then that we've got different MVA's ratings in the power system, we have to convert the percentage reactance of this, the percentage reactance found in this power system to the same base MVA. Why MVA? Because I see all units are in MVA. I'm gonna select a base of an MVA. It can be any value. It can be any value that you like. Why? Because that value has no influence whatsoever to the short circuit current. That is why in practice, I remember one engineer said, no, you can choose any value. It is unimportant. At the time, I didn't know why until I sit down and analyze it. So now I realize why he said this. That's why I say listening is very, very important. You choose any value. Why? It doesn't have any influence to the short circuit current. That's the reason. All right, because I don't have. So let's say assume a base of 10 MVA. This is the largest rating in this power system, and it is equal to what? The alternator. It is the percentage X alternator is equal to what? S base, this one, over the S rated, this one. I'm just giving you the difference between this 10 over 10. This is the selected one, and it is equal to the base MVA. This is the rated one, and it is the rating of this particular alternator, and it is 10. Multiply by the percentage reactance of this particular alternator, and it is 10%. And it is equal to what? 10 over 10 is 1. Multiply by 10 is equal to 10%. 10%. We are done there. We are now here. 5. It is out of a base of 10 MVA as base over the rated volt. Oh, very, very, very important. I just want to clarify this thing before I continue. You are given a transformer here, and you are told that it is a step-up transformer, meaning this is the low side, and then this is the high side. The voltage, meaning the alternator after the voltage has been generated, it supply a transformer a minimum voltage, and then that transformer stepped it up before it is supplied to the line. So this is the high voltage side, this is the low voltage side. That statement is very, 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 very extra important on this. You're gonna see why. Okay, and then it's 10 over 5 multiplied by the percentage reactance of this. It's equal to 10 divided by 5 is equal to 2. Multiplied by 5 is equal to 10%. 10%. We are done there. We come here. What happens there? We've got a resistance of 1 ohm. We've got the reactance of 4 ohm. But we want everything to be the same so that we can have easy calculations. Let's convert this. Let's convert this to the percentage resistance. Percentage resistance is equals to the base of 10 to the power 6 all over a voltage of to the power 3 squared multiplied by the resistance multiplied by 100% is equals to what? Is equals to what? Let's check faster here. Okay, right. It is 10 exponent 6 divided by 10 exponent 3 squared equals to multiply by 1 is 0.1 multiply by 100. It is equals to 10. Is equals to 10. Is equals to 10%. Here, percentage resistance is equals to 10%. Let's come here, same story. The percentage X here, X of the line, let's write it line, is equals to what? Is equals to 10 multiplied by 10 to the power 6 all over 10 multiplied by 10 to the power 3 squared multiplied by 4 multiplied by 100% to express the percentage, to express this 4% in terms of percentage. It is 10 exponent 6 divided by 10 exponent 3 squared multiplied by 4 is 0.4 multiplied by 100 is equals to 40% here. Percentage X here is equals to 40%. 40 percentage X is equals to 40%. Right. This is the line diagram. We have made calculations this way because I don't have space. Calculate the short circuit current fed to the symmetrical fault between phases at the load end, of the transmission line. There, at the load end of the transmission line. At the load end of the transmission lines. Let me erase this part, guys. Let me erase this part. I hope you have written this one, and it stands to reason that I'm gonna need this information. I'm gonna need this information for why? To calculate, to draw the reactance, the reactance diagram corresponding to the single phase line diagram derived from the information. Actually, I'm giving you the steps as to how to calculate the symmetrical faults. You draw the line, the single line diagram derived from the information. You assume a base, whatever base, but to me actually should always be equals to the largest rating in the power system. And then after that, you draw this reactance. You draw the line diagram of the reactance corresponding to this. That's what we are doing now. And it is equals to this. This one, let's say for argument's sake, this, it is our neutral point. And then from here, this one, it is this one. It is the percentage X of the alternator. And it is equals to what? It is equals to 10. Right, you are done. You come here. The transformer. Percentage reactance of the transformer. This one. Why? And it is equals to what? It is also equals to 10. Right? Okay, right. You were told that after the on the high voltage side of the transformer there's a fault, but don't worry about that for now. You are here, and then there is the resist percentage reactance percentage. This, it is the percentage R, and it is equal to what as well? It is equal to 10%. And then there you've got the percentage reactance of 40% here. And then this is where your line ends. But at the load end of the transmission line, you have to calculate the short circuit kVA there. And where else? At the high voltage side, like I told you there, it means this is alternator, and then this is the transformer there. You have to calculate the faults here and there. But the first condition says where? At the load end. Now, look. This one plus this one is how much? Okay, we are here actually. It's 10, this one, plus 10, this one, plus 40, this one. It's 60%. It's 60%. And then percentage R, this one is equal to 10%. There was only one resistance. Now, remember, this statement is very important. The first condition, it says at the load end of the transmission line. Here, listen to this statement. When a fault occurs at the load end of the transmission line, the impedance, or let me say the percentage impedance, is gonna impede that line from the alternator up to the point of fault there. And what is the impedance? Percentage impedance is equal to the phasor sum of percentage R is 10 squared plus percentage X. How much is X? It's 60. It's 60 squared. It's equal to what? It's equal to 10 squared plus 60 squared equals to second function square root. Answer 60.83. .83. This is the total impedance from the alternator up to the point of fault. From there up to there, including the impedance include the resistance. Right. Now then that we've got this, the short circuit kVA. The short circuit kVA is equals to the base kVA. To make things easy, this base kVA, if you multiply it by 100 over percentage Z or percentage X, you get short circuit kVA. And it is equal to what? It's equal to 10. It's equal to 10 multiplied by 10 to the power 3. Remember, it is 10 megavolt amps. 10 megavolt amps. To convert it to kVA, you divide by 1,000. So it was divided by 1,000 until it becomes 10 exponent 3. 10 exponent 3. Multiply by this over the total impedance of percentage impedance of 8.3. Therefore, short circuit kVA is equal to what? Is equals to 100 divided by 60.83 equals to multiply by 10 exponent 3. Answer is equals to what? Is equals to 16. Is equals to 16439.3 kVA. Is it kVA? Yeah, it's kVA. kVA, or it can be, if we divide again by 1000, it can be 16.43 megavolt amps. I can't remember whether the question was in kVA or what. kVA. The question was in calculate the short circuit kVA. Yes, this is the situation. But now they also say at the high voltage and meaning the impedance gonna impose the fault up to that point there, and it is equal to what? It is only 10 plus 10. We're gonna divide it by 20. We're gonna divide it by 20. It's gonna be divided by 20. Short circuit kVA from there to there is 20. Is 10 up to that fault there is 20. Is equals to 10 multiplied by 10 to the power 3 multiply by 100 over 20, and that's the answer. It's equals to what? It's equals to 100 divided by 20 is 5 multiply by 10 exponent 3 is equals to what? It's equals to 50,000 kVA. Very, very important. For this part actually should end there. We can extend it by asking you if you compare the high voltage side and the high voltage side and the low voltage side, where will you put circuit breakers of lower ratings and so on, and what type of the relay you think will shoot. But that's a discussion probably for tomorrow according to Mr. Akisana. Hi guys, again man, please an extra please man, subscribe, share the video, and this is bread and butter issues. Don't forget, for those already who got that information, on the 31st of October and the 1st of November we will be in Rustenburg. There's a GCC seminar there. Please man, book your seat. Only 30 people are welcome. It's 5,500. You're gonna see that 5,500 it's worth nothing compared to what you're gonna get. There's gonna be serious heavyweights there. Engineers, chief electricians, supervisors, people who have done problems for more than 20 years. He's got nothing, but he knows, he can see the systems. All those people will be there. You will even be given your own spare time if you want to ask questions. Please man, just go to YouTube and check what to do, but we'll talk about that maybe on the next video, probably tomorrow. See you then while you are subscribing. Sure.